Okay, so today we are going to start with some theorems related to operators. You remember that we have introduced the Hamiltonian operator that appears in the Schrödinger equation. But we also have introduced another operator that is the momentum operator that also is one of the building blocks of the Hamiltonian. So for the first part of this lesson, we shall see some properties of operators. There are things that very likely you have already met on other occasions. You remember that in considering some simple examples of application of the Schrödinger equation, we accepted the idea that the functions we are dealing with are complex. And we said this is no problem because the use of complex functions is somehow a simplification because the notation is simpler. And in any case, when we have to calculate the probability of localization of a particle or other probabilities that we shall see, following the recipe of quantum mechanics, we take the square modulus. So in any case, eventually we always have to deal with real functions because they correspond to physical properties. So the first concept that we want to introduce is a concept that generalizes the scalar product between two vectors. We introduce the scalar product between two functions. So we consider two functions f and g that are defined over a domain of the space coordinates that we indicate with tau. And these two functions are complex. So we multiply f by the conjugate of g. So the general rule for building up the scalar product is the function that stays on the right side of the product is taken as is. The function that stays on the left is conjugate. Then after constructing the product, we integrate over tau. So by definition, this integral is the scalar product of g and f. And it is usually indicated with the symbol that you can see on the left-hand side, with those parentheses with the tip. And the two functions are separated by a vertical bar. And when we use this symbol, we do not explicitly write down the asterisk, because it is implied that in the calculation, the function that appears on the left is conjugate. It may happen that the scalar product between two functions is equal to 0. So by analogy with the vector theory, in this case, we say that the two functions are mutually orthogonal. Then there are some rules that are very easily demonstrated. If you invert the position of f and g, so you take the scalar product of f followed by g, what you obtain is the conjugate of the original scalar product. Of course, the coordinates are real, so the space of the space tau is real in itself. If you take any complex constant b, and before carrying out the scalar product, you multiply f by b. Of course, b is a constant, so it goes out of the integral, and you get b times the scalar product. Instead, if you place b attached to g, you remember that those that stays on the left takes the asterisk. So you obtain b star multiplying g scalar f. The scalar product is a linear operation. So if you multiply scalarly g by a linear combination b1 f1 plus b2 f2, you obtain b1 times the scalar product of g with f1 plus b2 with the scalar product of g with f2. And similarly, if you consider the scalar product of two functions g and put it on the left, then you have b1 star times g1 scalar f plus b2 star times g2 scalar f. Let's now elaborate a little on this. Assume that you take a function f and you operate on it with an operator that is indicated with d. D is any operator, okay? So what is the result of the application of an operator onto a function that you obtain another function? So operating with d over f yields another function that we call, for instance, s. And then we take the scalar product of g with s. Okay, if you write it down explicitly, you obtain the integral of g star followed by d operating on f integrated over tau. If you do the opposite, that is, if you place s on the left of the scalar product, then you obtain d operating on f, all of it with a star, because everything that stays on the left takes the asterisk, times g integrated over the volume. When you consider an operator d, you may associate to it another operator that is indicated with the symbol that you see on the page. It looks like d with a cross, but it is not a cross, it is a knife. So it is called dagger. So this operator is called d dagger. Okay. So d dagger is an operator that is associated to d and has the following property that you see it below, that for any pair of functions g and f, the scalar product obtained by taking f, operating on f with d, then multiplying on the left by g and then integrating, is identical to the quantity that is obtained by starting from f and then multiplying on the left by d dagger operating on g. Okay. essentially, if you have an operator that is initially on the right in a scalar product and you want to transport the operator on the left without changing the value of the integral, then you must replace d with another operator that is d dagger. D dagger is also called the adjoint operator of d. In general, d dagger is different from d. But there is a class of operators that have the property that the adjoint is equal to the original operator. For some operators, this happens, and those operators take a special name. They are called self-adjoint, or also Hermitian. So a self-adjoint operator is an operator that is identical to its own adjoint. These definitions look abstract, but since you remember, we have a similarity of the scalar product in vector algebra. The scalar product of two functions is a generalization of the scalar product of two vectors. Also, the operation of an operator onto a function is the generalization to the continuous case of the multiplication of a vector by a matrix. And you remember that also for matrices it is important to specify whether the matrix is placed on the left or on the right in a product. The adjoint operator in the language of matrices is the transpose conjugate. Okay, so in the language of matrices, d dagger would be the transpose conjugate of matrix D. So you remember that if you take a vector f, you multiply by a matrix, and then you multiply the rest by G, the result by G, you obtain a number. If you instead multiply vector G by the conjugate transpose of D, and then you multiply the result by F, you obtain the same thing. Of course, we are dealing with complex vectors and matrices. When we have the self-adjoint or Hermitian operator, we have that G scalar D operating on F is identical to D operating on G scalar F. So for an Hermitian operator, it is irrelevant whether the operator is placed on the right side of the scalar product or on the left side. So sometimes you write it down as you see in the lower line of the page on the right, with two bars instead of one bar. Instead of one vertical bar, we use two vertical bars. And that means that it is irrelevant whether the operator is applied to the left or to the right. Let's check whether the Hamiltonian is Hermitian. So in order to check whether it is so, first of all, we select the Hamiltonian that we have considered so far. So we take the Hamiltonian of a conservative case that is in the form minus h bar squared over 2m Laplacian plus the potential energy V. Now, if the Hamiltonian is Hermitian, that means that we can, in a scalar product, we can place it on the right-hand side or on the left-hand side and nothing changes. That means that the two expressions that you see in the first line must be equal to each other. That means that the difference between the two expressions must be equal to 0. So in order to prove that the Hamiltonian is Hermitian, we must prove that the difference in the first line is 0. So we simply use the definition. The first block is visible in the first part of the integral in the second line. We have the Hamiltonian applied to function f. And then we multiply by g star. The other block, the other two terms in the second line are the Hamiltonian applied. The Hamiltonian in itself is real. So when you attach the star on it, nothing changes, okay? But when you apply it on G on the left, G takes the star. So we have the Hamiltonian applied to G star multiplied by F. So you see immediately that the product F V G star cancels G star VF. Then you collect all the constants and put them outside of the integral. So h bar squared over 2m, we are in the third line, multiplies the integral of what is left. And what is left is f Laplacian G star minus G star Laplacian f. There is a manipulation that goes under the name of Green's theorem, or one of the Green theorems, that tells you that we can transform this integral over the volume in an integral over the surface that is the boundary of the volume. So what we obtain is visible in the fourth line. It's h bar squared over 2m integral over the boundary of f times the derivative of G star with respect to the direction e normal to the boundary minus G star times the derivative of f normal to the boundary. Now there are two possibilities, as you remember. If the functions f and g are normalizable, then they go to 0 at the boundary. It doesn't really matter whether the boundary is at infinity or not. You remember in the box, the boundary was not at infinity, but yet in that case, the function is 0 at the boundary. Or if the boundary is at infinity and the functions are normalizable, then they go to 0. So the integral goes to 0 at infinity because f and g star independently go to 0 at infinity. If instead f and g are of the form, for instance, of the wave function of a free particle, by some other calculation, you can still demonstrate that the Hamiltonian is Hermitian. If somebody does not remember the Green theorems, they are, or at least the one that is of use here is outlined the bottom part of the page. Okay, you simply apply a vector identity. Divergence of f times a vector is f times the divergence of the vector v plus v scalar product gradient of f. Then you impose that v, that is a vector, is the gradient of another function that you call g. So you have the expression of the divergence of f gradient of g. Then you rewrite the same expression by interchanging f with g. And then you subtract the second expression from the first one, and eventually you find the last line, that is the relation that you find above in the integral. Conclusion: the Hamiltonian is Hermitian, and you can repeat the calculation with the momentum operator, and you find that also the momentum operator is Hermitian. Here we have a few definitions. You remember we already calculated two examples of the solution of the Schrödinger equation. In the example of the box, we found that the eigenvalues energy in energy are counted by an integer, index n. So we had E1, E2, etc. You remember that the set of the eigenvalues of an operator is called the spectrum of the operator. So in the case of the particle in the box, the spectrum of the eigenvalues is discrete because there is an integer index that counts the eigenvalues. Instead, we found that for the free particle, there was no limitation to the values of energy provided they were positive or non-negative, okay? So in that case, the values of the energy of the particle could change continuously. So in that case, the spectrum is continuous, okay? There is a third possible case that we did not examine. There are cases in which the eigenvalues are made of two sets. One set is continuous and the other set is discrete, okay? This may happen easily. So in this case, the spectrum is called mixed. Another comment is this: when you have the situation like that of the particle in a box in which you have one index counting the eigenvalues, you find one index because the problem is one-dimensional. If the problem was two-dimensional, you would find two indices. And if the problem is three-dimensional, you find three indices. It may also happen that, for instance, in a two-dimensional situation, one of the indices is discrete and the other is continuous. Okay, so you may have several combinations of this type. We also observed that in the case of the box, there is a one-to-one correspondence between the eigenvalue and the eigenfunction. In this case, the eigenvalue is called simple, whereas in the case of the free particle, the eigenvalue is the degenerate of order 2, because there are two linearly independent eigenfunctions corresponding to the same eigenvalue. It may happen that the order of degeneracy may be larger than 2. It may happen that there are like S linearly independent eigenfunctions corresponding to the same eigenvalue, and in some cases not so complicated. You may also have a degeneracy of order infinity. The considerations that we are going to do, or the definitions or the examples or theorems, apply in the same way to the discrete and to the continuous spectrum, but in many cases the demonstration is somewhat easier if you consider the discrete spectrum. So the majority of the demonstrations will be made considering the discrete spectrum. So let's consider this case. Take an operator and assume that this operator is Hermitian. We shall see later that the operators that we must consider in quantum mechanics must be Hermitian. And the reason is quite simple. The eigenvalues of the Hermitian operators are real. So we shall demonstrate this, not now, but later, okay? But let's anticipate that the eigenvalues of the Hermitian operators are linear. That means that if we want to consider situations of real life in which the dynamic quantities to be considered are real, like position, energy, momentum, and so on, since we shall see that the dynamic quantities in quantum mechanics happen to be the eigenvalues of differential equations, they must be real, okay? And in order to be sure that the eigenvalues, that are the physical quantities of interest, are real, we must consider Hermitian operators. Now, take an operator without specifying what operator it is. It is sufficient that it is Hermitian, and call it A. Okay. And then form the eigenvalue equation of this operator. So the general form of the eigenvalue equation is, as you can see in the second, in the dot, A applied to some function V must be equal to a number that we again call A multiplied by V. So V is the eigenfunction, and A on the right-hand side is the eigenvalue. We assume for simplicity a discrete spectrum. So the eigenvalue will be some A1, A2, etc. So two of them will be some A sub n and A sub m. So assume that these two eigenvalues are different from each other. If the eigenvalues are simple, there is one and only one eigenfunction Vn corresponding to An, and one and only one eigenfunction Vm corresponding to Am. If instead the eigenvalues are degenerate, there may be more than one Vn corresponding to An and more than one Vm corresponding to Am. It doesn't really matter. We may assume the degenerate case. So we say let Vn be one of the possible eigenfunctions corresponding to An, and Vm one of the possible eigenfunctions corresponding to Am. In any case, these two eigenfunctions fulfill the eigenvalue equation, so it is correct to write down, as we can see in the equation, operator A applied to Vn must be equal to the corresponding eigenvalue An times Vn. And similarly, operator Vm operator A applied to Vm must be equal to the corresponding eigenvalue Am multiplying Vm, okay? Now let's take the first eigenvalue equation, the one that corresponds to index n, and then we calculate the scalar product on the left with Vm. That means that we multiply both sides by the conjugate of Vm, and then we integrate over the space. In the right-hand side, of course, An is a number. It may be complex, okay? We don't know yet. But we can take it out of the scalar product, okay? So we obtain the first relation in the second line. Then we take the other eigenvalue equation, the one that applies to Vm, and we multiply it on the right, this time, on the right, by Vn. So first we take the conjugate of the equation, then we multiply it on the right by Vn, and then we integrate. Again, we must take out the constant, but in this case the constant is on the left, so it takes the star, okay? Now we subtract these two relations one from the other, okay? So we have the scalar product of Vm times Avn minus the scalar product of Avm scalar Vn. Obviously, these two scalar products are equal to each other. Why? Because by hypothesis, the operator is Hermitian, so we can freely transport the operator from left to right or vice versa in the scalar product. So the left-hand sides of the two relations are equal to each other, so they cancel down. Then we have that the difference between the two right-hand sides must be zero. We collect the scalar product, and we obtain that An minus Am star times the scalar product Vm times Vn must be zero. Now the point is that with a separate analysis, one can demonstrate that the eigenvalues of the Hermitian operators are real, okay? But if they are real, Am star is equal to Am. So actually, in the parentheses, we have the difference An minus Am. But we assumed at the very beginning that the two eigenvalues are different. So the parenthesis An minus Am is non-zero. So the only possibility left is that the scalar product Vm times Vn is zero itself. That means that the two eigenfunctions are orthogonal to each other. Conclusion, and this can be repeated for any choice of the numbers n, m. So the conclusion is that if we have an Hermitian operator, the eigenfunctions corresponding to different eigenvalues are mutually orthogonal. This is fundamental because, as we shall see, it eases very much a number of calculations. Okay. One may argue, how can we tell that the eigenvalues of the Hermitian operator are real? It's actually very easy because the relation that we have just found, an minus am star multiplying the scalar product of Vm times Vn, is still valid if you take the two indices equal to each other. There is nothing against it, okay? So let's try to take the two indices equal to each other. We have that Vn, scalar Vn, that is the scalar product of a function by itself, is the integral of the square modulus. But in this case, the scalar product is necessarily different from 0 because the eigenfunctions are the non-trivial solution of the eigenvalue problem. So the eigenfunctions are non-zero. Their square, the square modulus, is strictly positive, and the integral of it is also strictly positive. So when the two indices are equal, for sure, the scalar product Vn times Vn is non-zero. So in order to have that the total product is 0, we must have that an minus an star is 0. That is, an must be equal to its own conjugate. That is, an is real. So by the same analysis, we find that if you have an Hermitian operator, all its eigenvalues are real. And all the eigenfunctions corresponding to different eigenvalues are mutually orthogonal. And this is a very important theorem, and we shall use it many times. There is a point. Assume that the eigenvalues are degenerate. Okay, so to eigenvalues an, there correspond several eigenfunctions Vn that are linearly independent from each other. What happens if we check two eigenfunctions belonging to the same eigenvalue? Are they orthogonal to each other also? In general, they are not. So when one calculates the eigenfunctions belonging to the same eigenvalue, they are not in general mutually orthogonal. This theorem is applicable only to different eigenvalues, not to functions that belong to the same eigenvalue. So it looks like when we have degeneracy, then there are problems, but they are not, because there is a procedure that we are not going to describe in detail. This procedure is called orthogonalization. That shows that if you have a set of eigenfunctions that correspond to the same eigenvalue and they are non-mutually orthogonal, you can derive another set of equations from them that are still eigenfunctions of the original operator, but they are also mutually orthogonal. Okay. This is no mystery. You remember in the simple example of vectors, if you take a two-dimensional problem for simplicity, and you have two vectors that are non-parallel, but non-orthogonal either. Okay, so since they are non-parallel, they form a basis on the plane. And you can always manipulate these two vectors in order to find other two vectors that are, again, a basis, but also mutually orthogonal. So this is always possible with vectors, and this is also possible with functions, okay? So we may state that every eigenfunction of an Hermitian operator is orthogonal to any other eigenfunction that belongs to a different eigenvalue. And then every eigenfunction that belongs to an eigenvalue can be made orthogonal to the other eigenfunctions that belong to the same eigenvalue. So and they stay orthogonal with respect to the others belonging to different eigenvalues. So in conclusion, we may always state that all eigenfunctions of the Hermitian operators are mutually orthogonal regardless of being simple or degenerate. Okay? The name of the procedure for orthogonalizing is called the Gram-Schmidt orthogonalization. Okay, and it is very, very similar to that you can use in geometry using vectors. Another fundamental property of the set of the eigenfunctions of operators goes under the name of completeness. In order to introduce completeness, we take the very well-known example of the Fourier expansion. Okay, you know that the Fourier expansion is based on sine and cosine. And qualitatively, you tell that sines and cosines of a suitable argument can be used to reconstruct a function, okay, by a series. So they are complete. Okay, so we are now going to better specify the meaning of completeness. We start with the function f that is defined in some interval of interest. This interval is symmetric. For simplicity, is taken symmetric with respect to the origin. So the interval goes from minus alpha divided by 2 to plus alpha divided by 2. And then we assume that the function is good, meaning that its modulus is integrable over the interval, okay? So this is sufficient for the possibility of expanding the function into a Fourier series. And you remember very well that the expansion reads, as you can see in the first line, you have 1/2 A0, and this 1/2 A0 is the average of the function over the interval, plus a series in which have combination of sine and cosine with some coefficients that we call an and bn, and sine and cosine have an integer index n that goes from 1 to infinity, and then they have an argument that is 2 pi n x over alpha. As I said before, the zero order term 1/2 a0 is, by construction, is the average over the interval of the function. Okay, you remember that the equality of the Fourier expansion means convergence in the mean. Okay, because you remember this expansion is applicable also to functions that have discontinuities, for instance. Okay. So what does it mean? It means that if, for simplicity, we eliminate the average. So instead of considering f, we consider g equal f minus the average. Okay. The convergence in the mean has the following meaning. We take the actual function g, that is the original f less the average. Then we subtract a truncated expression of the series. So instead of summing over the index from 1 to infinity, we sum from 1 to some n, capital N. Then we take the square of the difference. So we obtain something that is non-negative. Then we integrate over the domain of the function. Again, we obtain something that is non-negative. And then, after integrating, we let capital N go to infinity. So we take an infinite number of terms of the series. If this limit is 0, we say that the Fourier expansion converges in the mean to the original function f or g in this case. Okay. The notation is inconvenient. So let's try to make it shorter. Instead of considering the symbol cosine of 2 pi n x over alpha times square root of 2 divided by alpha, we call all of this chi n. So chi n is just a shorter symbol for the cosine times that coefficient. And in the same way, we introduce another symbol sigma sub n, that is sine of 2 pi nx over alpha times square root of 2 over alpha. So we have a set, two sets of functions, chi and sigma. We can immediately check that if we take any one function from one set and any function from the other set, these functions are 2 by 2 orthogonal. So each of the cosines is orthogonal to each of the sines, regardless of the index, for any index, including 0 up to infinity. So these two functions, two sets of functions, chi and sigma, constitute two sets of mutually orthogonal functions, but there is more. Each sigma is also orthogonal to each other sigma with a different index, and each chi is also orthogonal with each other chi of a different index. So all these functions are, no matter how we choose them, are mutually orthogonal. Also, if we take sigma and multiply scalarly sigma by itself, you obtain 1. And similarly by taking chi. Okay, so the two sets, chi and sigma, actually form a single set of functions, and these functions are mutually orthogonal. Any pair of them is orthogonal. And they are also normalized to 1. Okay, so we start seeing in the properties of the functions that are used for the Fourier expansion, we start seeing some properties of orthogonality and normalization that we have introduced in quantum mechanics. Now we stop because it is already finished. We shall resume in 10 minutes. Okay, let's continue with the topic of completeness. We have introduced the Fourier series, very well known, and then we have described the set of functions as a set of functions that are mutually orthogonal and also normalized to 1. When we have a set with these properties, we also call it orthonormal, orthogonal and normalized. In addition, we know that in the case of the Fourier series, this limit is 0 if the original function has the property of being integrable in modulus over the domain, okay? So when this limit goes to 0, we say that the Fourier series represents the function in the average, okay? Because essentially we obtain the 0 by taking the limit of an integral, okay? When this happens, that is when the series converges with the meaning of that limit, we say that the set of functions sigma and chi is complete. Okay. So this is the meaning, the formal meaning of completeness. Now the issue is, can we express all of this in a more compact form? Yes. We start by considering the expressions of the coefficients of the Fourier expansion. You remember the expression of the coefficients is given in the first two lines of the page. The coefficients of the cosine an are 2 over alpha. You remember that alpha is the total length of the domain where the function is defined. 2 over alpha times the integral of the cosine times f. And similarly, bn is 2 over alpha times the integral of sine times f. But those are scalar products. Okay? Sine and cosine are real functions, so it doesn't really matter to consider the conjugate because they are real, so they are placed on the left. So we can call an, we can call it chi n scalar product f. And then we go back to the original form of the Fourier series, okay? An, that is the scalar product, is in turn multiplied by the cosine that is proportional to chi n, okay? So the conclusion is that the Fourier series can be expressed in more compact form as the average f times a series whose terms are chi n multiplied by a number that is the original an, expressed as the scalar product of chi n times f. And similarly, the block with the signs is sigma n times the scalar product of sigma times f. So if we take again G instead of F, we have that G can be expressed, as you can see, in the middle of the page. Then we give this expression an even more compact form, okay? Assume that you have written all terms one after the other. So you have the term with chi1 followed by the term with sigma 1. Then you have the term with chi2, that is the third, followed by sigma 2, that is the fourth, and so on and so on. So all terms embedding chi are in the odd position in the sum, and all terms embedding sigma are in the even positions of the sum. So we can use these other symbols. We call W2n, you can see it here, equal to sigma. That is, all the functions W of even order correspond to the sigmas, and all the function W's of the odd order, 2n minus 1, correspond to the chi functions. And then we have the coefficients, those of odd orders, C2n minus 1 correspond to chi n times G. And those of even order, C2n, correspond to sigma n scalar G. So finally, the expression of the Fourier series that is in the middle of the screen, in which we still distinguish sine and cosine, takes the very compact form that you can see on the bottom. It is a sum of coefficients, and each coefficient multiplies a function W. And moreover, each coefficient is the scalar product of Wm times G, times the original function. Now, you see a very strict similarity of this expression with the expression of a vector using the components. You may think that Wm is one of the components of vector G, and Cm is the coefficient of the component. And in turn, Cm is the projection, that is the scalar product of the component times the original vector. So this is identical, with the only difference that the sum goes to infinity, because there are infinite terms in the series. So the only difference is this. If you take a vector space of finite dimension, you have a finite number of components. Okay, in this case, you have an infinite type of component. So, in conclusion, the result is that the Fourier expansion, that is the example of completeness, based on the example that is very well known, because the completeness of sines and cosines can be demonstrated, okay, can be recast in a form that looks like the expression of a vector in terms of its own components. And the components are the projections of the vector onto the, we can call them unit vectors at this point, okay? Now the question is, are functions sine and cosine that appear in the Fourier expansion the only possible functions that form a complete set, And the answer is no. In mathematics, there are many possible sets of functions having the same properties as sines and cosines in this respect. That is, these sets of functions are complete in the same sense that we analyze for the Fourier expansion. And also, all elements of these sets of functions are mutually orthogonal. They are orthogonal with the other functions and can be normalized to 1. And moreover, it happens that when we, in quantum mechanics, consider an operator, and then using this operator, we build up an eigenvalue equation, and then we find the eigenvalue and the eigenfunctions, then we can check and find that the set of eigenfunctions of the operator form a complete orthonormal set. Okay, this is not for granted. This must be demonstrated, but mathematicians have worked a lot on this. So we know that the sets of functions that come out from the operators using in quantum mechanics are have these properties. Okay, and these properties are very important. Why? Because if we have a complete set at our disposal, we can form, by a linear combination like the Fourier series, we can form a function. We can express a function using the expansion into the complete set that we have at our disposal. The second important property is that the elements of this set are orthonormal. And this is very useful for the calculations, as we shall see. It's like having a reference in which you have unit vectors that are normal to each other. So the projections are very easy because they are 2 by 2 orthogonal, so the scalar product are all 0, essentially, okay? And this is very convenient for the calculation, okay? So can we make a correspondence between the concepts of completeness and orthonormality that we have found for the Fourier series with some results that are known to us already of quantum mechanics? Well, yes. You remember when we solved for the Schrödinger equation of the particle in a box, we found that the normalized eigenfunctions are, as you can see in the second line of this page, square root of 2 over alpha sine of 2 pi nx over alpha. But these are exactly the sigma functions that we have used in the analysis of the Fourier transform, okay? So the set of functions that we obtain from the problem of solving the Schrödinger equation for the particle in a box is made of the sigma function. The chi functions are not there. They do not come out from the solution, but this is very simple. We can just double the integration domain and impose that the function is odd. It's very easy. So we eliminate all the coefficients in front of the cosine terms. Okay, so the set of the cosine terms for the problem of the box is not important, should not be used because all the coefficients are 0. Okay. So this is the first example. The second example is the example of the free particle. Remember that for the free particle, we have found that given the eigenvalue E, that is the energy, that is some positive value, we construct K, and then the two eigenfunctions are exponential of j kx and exponential of minus j kx, v plus and v minus, okay? We may manipulate a little bit the result by saying, instead of taking two functions in which we consider a positive k and then we put the plus sign in one case and the minus sign in the other case, we may say let's k have any possible sign, positive or negative, and then let's consider only one form of the eigenfunction, that is exponential of j kx, in which k can also be negative. So we obtain the same set as before with a more compact symbol, okay? You also remember that for the free particle, the situation is such that the wave function cannot be normalized. So it is always defined apart from a multiplicative constant, okay? So let's take the constant equal to 1 over the square root of 2 pi, okay? Conclusion, exponential of j kx over the square root of 2 pi is just the function that appears in the Fourier transform, or in the entire transform, actually, because we have a plus. So we are sure that an expression in which look at the last line, okay? The second equality on the last line expresses f of x as the exponential of j kx over 2 square root of 2 pi times the function c of k. And for the properties of the Fourier transform, c of k is the Fourier transform of f that you can see on the left on the same line. So you define c of k as the Fourier transform of f, and conversely, f is the anti-Fourier transform of c. We know that these two expressions are correct if f is integrable in modulus, in this case over an infinite interval, okay? So we assume that it is. Conclusion, we can use the exponential of j kx to represent a function. So this exponential is also a set of complete functions. In this case, the index is not an integer index anymore. The index is continuous and it is k. And you remember k depends on E, that is the energy, and is also continuous, okay? So exponential of j kx is the eigenfunction of the Hamiltonian for the free particle. So we have a second example in which we can say that the eigenfunctions of the Hamiltonian form a complete set. If we want to write it in short, we can use the shorthand, the compact notation that is visible above. We can write f as the integral from minus infinity to plus infinity of some c of x w of k of x, in which, again, c is the projection of F over Vw, and Vw obviously is the exponential of jkx over the square root of 2 pi. So again, we don't have the sum anymore, we have an integral, but that is another example of completeness of a set of functions, and these functions are the eigen functions of the Hamiltonian. These are easy examples because exponentials or sines and cosines are something that we are accustomed to, okay? In other situations with a different type of Hamiltonian, and of course we may have infinite types of Hamiltonian because when we start placing the potential energy in it, we have infinite possible choices for the potential energy. In all cases, the result is a set of eigenfunctions that are mutually orthogonal, normalized to one, and complete. Okay, so we shall exploit very much these properties for the calculations. Let's go back to the case of the discrete indices, okay? Let's expand a function that in general is complex in a complete set of functions Wn. So these functions form a discrete set that is complete, and also assume that they are orthonormal. So they are normal to, orthogonal to each other and normalizable to one. Then the coefficients, as you remember, are the projections of f onto the W functions. So they are the scalar products Wn times f. How do we express in compact form the property of these W functions of being orthonormal? We use the symbol of Kronecker, delta nm. You remember, delta nm is equal to 1 if the two indices are equal. It is 0 if the two indices are different. That means that Wn scalar product Wm with a different index is 0, that is, they are normal to each other. When m is equal to n, we have that the square modulus of Wn integrated over the domain is equal to 1, that is, the function is normalized to 1. Now let's take the squared norm of f. What is the square norm of f? Of course, we take the square modulus of f, and then we integrate it over the domain. Okay. In the language of the scalar products, we can also recast this expression as the scalar product of f by itself. But then we can express each term of the scalar product with a series. Of course, we shall use the expansion using the orthonormal system W. Okay, so on the left we have the sum over n of Cn Wn. On the right we have the sum over m Cm Wm. We use two different indices because otherwise they would get mixed. Okay, so the symbols for the two indices must be different. And then we simply perform the calculation by considering the properties of the scalar product. So you remember the coefficients that are on the left may come out, but they take the star because they stay on the left. And those that are on the right do not. So we have the sum over n Cn star followed by the sum over m Cm, and they came out of the scalar product. And then we have the scalar product of Wn times Wm, but this is a Kronecker delta. So the Kronecker delta essentially kills all the pieces of the internal sum with the exception of one, the one whose index m is equal to n. Okay, so the internal sum, the one that is added up over index m, actually reduces to one term, that is Cn. And Cn is multiplied by Cn star, so you get the square modulus of Cn summed over n. This is a fundamental result because we started from the squared norm of the function, and using the expansion, we demonstrate that the squared norm of the function is equal to the squared norm of the coefficients added up over the index. It looks odd because we start with an integral and end up with the sum. But this is only because we are using a discrete expansion. Okay, if we repeat the analysis, we shall do it in a second. Okay, using a continuous expansion, we find that the integral is equal to another integral. Okay, so let's do it again using an expansion. Instead of using a discrete index, we use a continuous index. Okay, so it is written here. You see the similarity. When we use the expansion in a continuous set, instead of the sum over n, we have the integral over alpha. Alpha is the parameter that replaces n. It could be k. In the last pages, it was k. Okay, remember in the Fourier transform, we integrated over k. So we have integral of C of alpha, W of alpha over D alpha. The integral is over the set of the domain of the parameter alpha. The projection is just the same as before. C of alpha is the scalar product of W alpha times F. The orthonormality condition is a little bit tricky because the quantity that corresponds to the Kronecker delta in the continuous case is the Dirac delta, okay? But you remember the Dirac delta is dangerous. It should not be used as is. The Dirac delta has a meaning only if you use it inside an integral, okay, not by itself. But in the next line, we are going to use it inside an integral, so we are safe, okay? So in the second line, we start as before calculating the square norm of f. We write it as the scalar product of f by itself, and we just perform the analysis. In this case, instead of the sums, we consider integrals, and in order not to mix the symbol, one integral will be over some parameter alpha, and the other one with the parameter beta. Okay. Then we extract something that does not depend on beta, so we extract C alpha star, and the inner integral has the delta. Okay. Obviously, because of the properties of the Dirac delta, the inner integral must be equal to C alpha. The parameter beta of C takes the value in which the argument of the delta vanishes. Okay, so beta must be equal to alpha. But the integral becomes C alpha that is multiplied by C alpha star. So we have, this is a perfect identity, a perfect symmetry of symbols. The integral over the coordinates of the square modulus of f equals the integral over the parameter of the square modulus of the coefficient. You remember that it is not necessarily true that alpha is a single parameter. It is a single parameter if we are in a one-dimensional case, but in a three-dimensional case, as we are here, alpha is actually 3 parameters, okay, like R. So we have a total symmetry of the equality. And that shows that the norm of the function is equal to the norm of the coefficients of the expansion. There is exact symmetry in this, okay? This is something that you may have heard in Fourier analysis, okay? That the norm of the function is equal to the norm of the transform, okay? But this is more general, because we are not anymore just in the Fourier analysis. We assume that we have a complete set of orthonormal functions that we are using for the expansion. They are not necessarily anymore the functions that are used in the Fourier analysis. Okay, so this result, in which we have demonstrated that the norm of a function is equal to the norm of the coefficients, is called the Parseval theorem. Parseval. Okay. And we conclude this page by giving some names, okay? When we have a scalar product, you remember the similarity of the scalar product of two functions with the scalar product of two vectors, okay? Formally, when you have the scalar product of two vectors, the vector that is on the right must be thought of as a column vector, okay? And the vector that is on the left must be thought of as a row vector, okay? We never care about this, but in principle it is so, okay? We can introduce a similar nomenclature and a similar notation for functions. We may think that the part of a scalar product that is on the right is a vector that is called cat. So the vertical bar f and the parenthesis with the tip on the right is called cat vector. And the first part of the scalar product, that is the tip parenthesis pointing to the left G followed by the vertical bar, is called a bra vector, okay? bra and cat are just the two pieces of bracket that is the form of the parentheses, okay? So this is the so-called Dirac notation that is very much used in quantum mechanics, the bra vectors and the cat vectors. Given that we are finished with the definitions and discussion about completeness and orthonormality, now we must take one step from the status of the matter that we left with the examples of the free particle and the example of the box. In those examples, if you remember, we assumed that the total energy of the particle was given. Okay? So we assumed that we possessed some knowledge of energy. And actually, we possessed a full knowledge of energy because we did know the value of energy. Okay. Actually, energy is one of the possible dynamic properties of the particle. Okay. So we must generalize a little bit the analysis by considering that we may not know the energy of the particle. We may still know that in general, the physical problem that we are considering is conservative. So we know that some total energy does exist, okay? But we do not have enough information about the particle or about the system to be sure that it belongs to a definite value of energy, okay? So we must now consider a more general case in which we have to deal with a conservative case whose energy is not known a priori. So it is not possible anymore to write the wave function as the product of the space part to be found from the Schrödinger equation and of the time part that is the exponential of minus j omega t. Okay, so we have to generalize the analysis. This generalization is possible, relatively easy, if we exploit the analogy with a similar case of the electromagnetic field. I remind you, the quantum mechanics, the wave function of quantum mechanics is not something that belongs to the electromagnetic theory, it's another thing. It's a distribution of probability, okay? But anyhow, some analogies exist, and if they exist, they must be exploited. We shall see this in the next hour. Now we stop, and we shall start again at 5:40. Sorry, I made a mistake. It's still 5:20. We still have 10 minutes. So sorry. We continue. Don't go away. Okay. So how do we perform the analogy? This is relatively easy because Consider the example of the monochromatic electromagnetic field, which qualitatively corresponds to the monochromatic wave function in which the energy is completely defined. What is the possible generalization in the electromagnetic theory of this case? The possible generalization is that of an electromagnetic field made of the superposition of many monochromatic waves. So the idea is we may try to see whether the generalization of the monochromatic wave function can be achieved by considering a superposition of monochromatic wave function. So in this case, we are essentially taking a more general form of the wave function for a conservative case. Instead of having one monomial expression with the space part times a time part, we have a sum of summands of this form. You see immediately that if we accept this procedure, and this procedure must be accepted because the conclusion turns out to be correct, okay? If we accept this conclusion, essentially, we are prescribing the most general form of the wave function of the conservative case as a superposition of monochromatic waves. In doing so, instead of saying there must be an equation, then we solve the equation and find the function, we are doing the opposite. We are prescribing the form of the function by generalizing the monochromatic case. And after doing that, by calculation, we deduce, or we shall deduce, the differential equation such that this new, more general function is the solution. So it is like an opposite procedure. Instead of looking for an equation to solve, solving it and finding the wave function, we impose the form of the wave function, and later, after having accepted the wave function, we find the form of the equation. Obviously, this is a postulate. And the postulate is easily expressed in the equation that is the first in this page. We postulate that the general wave function corresponding to the conservative case is the sum of monochromatic wave function. You see that inside the sum we have W that, as usual, depends only on position and is the space part of the summand that is present in this sum. The exponential of minus j e sub n t over h bar, as usual, is the time part. And then we have Cn. Cn is coefficient. In general, it is a complex coefficient, okay? Because the global wave function is a linear combination of monochromatic wave functions. This is just a postulate, okay? But it works, okay? So it leads to the correct conclusion. the general wave function of the conservative case is a linear combination of monochromatic wave function. Now the issue is, but what are Wn and E sub n? This is the question. The answer is Wn and E sub n are the eigenfunctions and the eigenvalues of the Schrödinger equation of the Hamiltonian. That is, the forces are conservative, and we know them. So we can construct the Hamiltonian. The Hamiltonian is made of the kinetic part, as usual, plus the potential energy. And in this case, we know the potential energy because we assume that this part of the problem is given. Then we construct the Hamiltonian, and by the Hamiltonian, we construct the time-independent Schrödinger equation. In this line, for simplicity, we are assuming that the eigenvalues are discrete. Okay, so they depend on the index n. We solve the Schrödinger equation independent of time. So we find the set of eigenvalues E sub n and the set of eigenfunctions W sub n. Then we place these functions Wn and these numbers E sub n in the expansion and claim that this is the general wave function of the problem, in which the coefficients for the moment are not known. They are the coefficients, the complex numbers that help in building up this sum. Okay? Obviously, this expression of the wave function is valid at every time. So in particular, it is valid at t equal to 0. But if we let t equal to 0, we find the expression that is in the second line, the second equation. Psi at t equal to 0 is essentially the sum of Cn Wn. But we know how to find the coefficients of a function that depend on position, because that is nothing else than the expansion of a function psi of R0 into a complete set of eigenfunctions W. So we find the coefficient Cn of the expansion by taking the scalar product of Wn by psi at t0. Conclusion, now we really stop because it is 5:30. In order to know the coefficient Cn, we must know the function psi at t equal to 0. So we must know the initial condition of the problem. If we know by any means, for instance, because we have taken a measurement, the information sufficient to calculate these scalar products, we know the wave function in full at every time, because we calculate the coefficients of the expansion and then we calculate the general expansion and at every time. And the ingredients W, N, and E sub n are provided by the Schrödinger equation independent of time that we build up because we know the potential energy of the specific problem. So now we stop and we shall continue in 10 minutes. Okay, now we are back to the case of the superposition of monochromatic waves. As I said before, this form of the wave function is taken as a postulate. So it is called the superposition principle. And it is derived from the analogy with the electromagnetic field that can be understood as a superposition of monochromatic waves. Okay. We also incorporated into the postulate that the function Wn and the energies E sub n that appear in the linear combination and are derived from the solution of the Schrödinger equation independent of time. This form applies, obviously, if the eigenvalues of the Schrödinger equation independent of time are discrete. And we are using this case because it is more easily manipulated, okay? But the same situation can be used in the case where the Schrödinger equation independent of time has a continuous set of eigenvalues. If that happens, we must, instead of considering the sum over index n, we must consider the integral over the continuous parameter. Then, how can we calculate the coefficient Cn? We can calculate the coefficient Cn if we have the information about the form of the wave function at the initial time, t equal to 0, because we simply find that we have the standard expansion of a function independent of time in terms of the eigenfunction Wn. Okay, so the coefficients are the projections of the wave function at t equal to 0 onto the eigenfunction Wn. For the moment, we did not ascribe any meaning, any physical meaning to the coefficients, but we shall see very soon that they also do have a physical meaning. The general form of the wave function is useful because, if you remember from the electromagnetic theory, that the interference of monochromatic waves allows you, using the superposition, to construct any form of the function. Okay? A simple monochromatic function is just monochromatic. There is nothing else you can do. But if you have many monochromatic waves available, by suitably choosing the coefficient, one can construct, for instance, a function that is called a wave packet. A wave packet is a function such that the square modulus of it is non-zero in some region of space and goes to 0 when we go away from that region of space. So it is something that is better suited for describing the localization of the particle. Another observation is that, as we already noted, the coefficients Cn are completely known if we know the initial condition of the wave function, so that the wave function in full is completely known if we know the initial condition, because all the rest of the ingredients E sub n, Wn are derivable from the Schrödinger equation. Okay. So this is an important issue, because if we imagine that there is somewhere an equation, a differential equation, from which we can derive the wave function of the general form here, if we understand that the wave function is uniquely determined by an initial value, we must conclude that such a differential equation must be of the first order, because only an equation of the first order with respect to time is such that knowing the initial condition in time is sufficient to know the function at all later times. A final observation is that in the sum that defines the wave function, we have that all energies are represented. So this wave function does not describe a motion with a definite energy. It describes something more general in which all energies are present. Okay. This postulate works. Okay. The experience shows that this form of the wave function is the correct form. So we are encouraged now to proceed and try to find the differential equation such that this function is the solution of such an equation. Before we do it, we extend the discussion a little bit. You remember the meaning of the wave function. The meaning of the wave function in general, assuming that the normalization is possible, is that the square modulus of psi at some instant of time t provides you with the probability density of the localization of the particle. Okay. We also know that the Parseval theorem applies. So we know that the integral of the square modulus of the wave function is equal to the sum of the square moduli of the coefficients. And since the function is normalizable, this number must be equal to 1. This is a very, very important observation. The equality integral equal to the sum comes from the Parseval theorem. That the sum is equal to 1 comes from the normalization. Okay, so we have a set of numbers, of complex numbers, such that their squares add up to 1. Now, assume that we have a particle that is described by this wave function, and that we start a measurement of energy. Energy is one of the possible dynamic quantities, so it is sensible to measure energy. We start at some time, and you remember the measurements take time. Okay, so we assume that there is a time that we call T sub E, in which the measurement of the energy is completed. When the measurement is completed, we have found one and only one value of energy, because we are measuring energy and we assume that we can measure it with arbitrarily large precision. Okay, so we have found one specific value of the energy. Okay. We shall see in a second that this energy must be one of the eigenvalues of the Schrödinger equation independent of time. But for the moment, let's call it E sub m. Okay. If we know for sure that the energy of this particle is E sub m, then the wave function that describes the particle from now on must be monochromatic, because now we know the energy. Before measuring, we did not know the energy, but now we know it. Okay. So from the instant of measurement on, the wave function, you remember, we say it contracts. It contracts to the monomial form in which we have only one exponential instead of the sum, okay? And this exponential must contain only the energy that we have just measured, okay? You see, we have reset the initial time at TE. So from that time, the wave function has a time part that is the exponential of j minus j e sub m t minus te over h bar. Okay. Why must the energy be equal to one of the eigenvalues? Because this function must fulfill the Schrödinger equation independent of time. The particle is still inside the force field that derives from the potential energy that we know. And this potential energy is inside the Hamiltonian. So when we solve the Hamiltonian, we find the possible energies, okay? So we must be consistent with the force field that is present in the region of space where the particle is, okay? So the energy must be one of the eigenvalues of the equation, E sub m. And the space part of the wave function necessarily must be the eigenfunctions that corresponds to that eigenvalue. So you see, the process of measuring has transformed the original form of the wave function, that is a sum of terms, into a function that has only one term, okay? But we know that originally the coefficients of the expansion were such that the sum of the square moduli of this coefficient were equal to 1. After the measurement, we have only one coefficient because we have only one term. Of course, this coefficient must have the square modulus equal to 1. Okay? So we don't write it down. We don't write C sub m in front of it. Okay? Why? Because the square modulus is equal to 1, and C sub m is the complex number whose phase is irrelevant, because the only part of it that matters is the square modulus. Okay, so we can set the phase of the coefficient Cm equal to 0. Okay, so before the measurement we had all coefficients, and the square moduli of them summed up to 1. After the measurement of energy, we have only one coefficient, and of course its square modulus is equal to 1. Okay? Before the measurement, we did not have much information about the energy. The energy could be any of the values E1, E2, E3, and so and so. After the measurement, we know for sure that the energy is E sub m. And we know that the square modulus of Cm is equal to 1. So we may, at this point, try to attach a physical meaning to the coefficients of the expansion. We may think that the square modulus of Cn, the general coefficient of the expansion, is the probability that a measure of energy finds the corresponding eigenvalue E sub n. Why may we say so? Because the square moduli of the Cn add up to 1. And of course, we know that when we measure, we must find either one or another of the possible outcomes. So the sum of these numbers must be equal to 1. That is certainty. Before measuring, we can only talk about probabilities. After measuring, we know with certainty the value of energy. So the corresponding coefficient E sub m must have the square equal to 1, because we are sure that this is the energy, the index of the energy. All the remaining coefficients whose index is different from m are set to 0 by the operation of measuring. So in conclusion, the measurement is like a filter. It's like a filter that out of a function made of the superposition of many monochromatic terms, filters out one of them and kills all the remaining ones. Okay? So we interpret the coefficient Cn squared as the probability that a measurement of energy of the energy of the particle will find the result E sub n. So we start giving a physical meaning to the terms involved in the expansion. Now we are ready to calculate the form of the differential equation whose solution is the superposition. Okay, so we, as I said before, we postulate that the superposition is correct, and then we try to derive a differential equation such that the superposition is its solution. It is quite easy because again we consider the case of discrete eigenvalues. Okay, the analysis can be repeated exactly in the case of a continuous set of eigenvalues. We take the derivative with respect to time of the wave function. Of course, we have the sum of Cn, Wn, because they do not depend on time, and then we take the derivative of the exponentials. And of course, it is the exponential itself times E sub n divided by h, and then it is multiplied by minus j, but we can place j in the denominator, so we eliminated the j. Okay. Now we have a very important observation. Inside the sum, you see there is the product En times Vn. Okay. But this product, because of the Schrödinger equation independent of time, is equal to the Hamiltonian applied onto Wn. So we can replace the product En times Vn, Wn with as you see in the second line, H applied onto Wn. This looks silly because we are replacing a constant that is E sub n with an operator that is complicated. But the constant depends on the index, so it must stay inside the sum. Instead, the operator is independent of the index, so we may take it out. And when we take it out, we see immediately that what is left in the sum is again the wave function. Because we have h that goes out, and then we have sum of Cn w exponential. So this is it. We have found with no effort a differential equation that is of the first order with respect to time, as should be. Remember, we noticed that. And the space part of the differential equation is again given by the Hamiltonian. So this equation is J(h bar time derivative of psi equal to Hamiltonian applied to psi. Okay? This equation is called the time-dependent Schrödinger equation that provides the time evolution of the wave function starting from the initial value. So as far as time is concerned, we have the initial value, and that's it. As for the boundary condition in space, obviously we have to use the same boundary conditions that we would use in the time-independent equation, because the operator that operates on space is still the Hamiltonian. Okay, so in general, we apply the vanishing of the wave function at infinity. Okay. Is this enough? No, because we have extended the analysis, but still to the case of the conservative situation, okay, in which we have the possibility to solve independently the Schrödinger equation independent of time, okay? Let me comment a little bit more on it. Assume that somebody gives you the Schrödinger equation that depends on time, the one that is written here on this page, okay? And asks you to solve it, okay? So the first thing that one should look at to solve this equation is to check whether the equation is separable. That is, whether we can separate space from time. Okay, separation is a formal procedure. We shall see it maybe next time. Okay. The outcome is we can separate time from space if the situation is conservative, because if the force field that acts on the particle is conservative, then the potential energy that appears in the Hamiltonian depends only on the coordinates, and there is no time in the Hamiltonian, okay? So if we have a conservative situation and we start from this equation and go on in the solution, we separate this equation into two blocks, and one block is the time-independent Schrödinger equation, okay? However, in physics, there are also problems that are non-conservative, okay? For several reasons. For instance, because the forces depend on the velocities, okay, like in the electromagnetic field. Or because the Hamiltonian has some explicit dependence on time, okay? So if that happens, the time-independent Schrödinger equation does not exist anymore in the non-conservative case, okay? That equation disappears, okay? So how should we deal with the non-conservative cases? We introduce another postulate. And the other postulate is that the Schrödinger equation depending on time, the one that is visible in this page, and that was derived from the conservative case, is more general. It is applicable also to the non-conservative cases. This is a postulate that again proves correct. Okay, so the time-dependent Schrödinger equation is even more general than what we believed at the beginning. It is applicable also to the non-conservative cases. In those cases, we can still write the Hamiltonian, but the Hamiltonian may depend on the velocities or have explicit dependencies on time, okay? So the equation is not separable anymore, okay? So if we have these more general problems, we can still use this equation. It will be more complicated to solve it because we lack separability, okay? Whereas we do not have anymore the Schrödinger equation independent of time. Now we open a parenthesis. Still assuming that we are considering the Schrödinger equation dependent on time, and we try to manipulate the equation in order to derive some information about the localization of the particle. You remember that the localization of the particle is associated to the square modulus of the wave function. So this square modulus is like, if you allow me the description, if you consider a wave packet, it's like a blob that moves in space. Okay, so it is a volume that is not point-like, but somehow gives you some information about the position of the particle. Okay, this is a wave packet as we conceive it for the description of the localization in quantum mechanics. So the idea is, can we extract some information from the Schrödinger equation in order to see how the square modulus of the wave function moves in space? The answer is, let's try. That is, we take the square modulus of the wave function, and in order to see how it moves in space, we take the time derivative of it, okay? And then we try to see whether there are some relations that are useful from this calculation. So what we do is we calculate the square modulus, and then we take the derivative of the square modulus. This is a pure calculation, because obviously the square modulus is equal to psi star times psi. So we have a product of two things. So we take the derivative of the product that becomes psi star times the derivative with respect to time of psi plus psi times the derivative with respect to time of psi star. Then the derivative of psi with respect to time is found from the Schrödinger equation. You remember the derivative with respect to time multiplied by JH bar is the Hamiltonian applied to psi. So the derivative alone is the Hamiltonian applied to psi divided by JH bar. So this term becomes this term. Then we have the derivative with respect to time of psi star, okay? And to find it, we have that we take the conjugate of both sides, okay? When you take the conjugate of j, you get minus j, okay? You remember the conjugate of j is minus j. On the right-hand side, we have psi conjugate. We assume that the Hamiltonian is real, okay? So the conjugate of the Hamiltonian is the Hamiltonian itself. So we have minus, because j becomes the conjugate, psi Hamiltonian psi star over jh bar, okay? Then we take out the constants, jh bar, and we have, you see, psi star Hamiltonian psi minus psi Hamiltonian psi star, okay? At this point, we must say something about the Hamiltonian. We take the standard Hamiltonian made of the kinetic part plus the potential energy independent of time, okay? So obviously, the part of this calculation in which the potential energy appears is purely multiplicative, so that two terms cancel each other. So we are left only with the kinetic part, okay? So the kinetic part, you remember, is minus h bar squared over 2m Laplacian. And here we have minus Laplacian of psi star, okay? And then we replace this quantity in the original equation on the first line, okay? You see that we have h bar squared, but then we have h bar in the denominator, so there is only one h bar surviving. And then we have j in the denominator. We can bring j to the numerator and change the sign, okay? We again use the green identity. So this combination of Laplacians becomes the divergence of psi star gradient of psi minus psi gradient of psi star. So eventually we put back the coefficients, and in conclusion we get this equation that is the derivative with respect to time of the square modulus of the wave function plus the divergence of some vector that we call j sub psi is equal to 0. What is that vector? That vector is jh bar over 2m psi gradient of psi star minus psi star gradient of psi. This j is real. Why? Because in the parentheses that define J, the two terms are, one is the conjugate of the other. Psi gradient of psi star is the conjugate, of course, of psi star gradient of psi, okay? So the difference of two complex quantities that are conjugate is 2 times the imaginary part. So there is a J as a factor, and this J cancels the other J that is outside of the parenthesis. So eventually, J is real. What is the meaning of J? Well, you see immediately that the the equation that we have found has exactly the appearance of a continuity equation. So the Schrödinger equation, that was the only ingredient used to derive this result, is such that after manipulation we can transform it into a continuity equation for the probability density. It follows that if this is the continuity equation for the probability density, you remember what happens when you have the continuity equation for particles. Instead of psi modulus square, you have the concentration of the particles, so the number of particles per unit volume. Here you have the probability per unit volume. And in the continuity equation for the particles, J would be the flux. So in this case, J is the density of the probability flux. Same thing, okay? So J psi is the density of the probability flux. You see that it contains the first derivatives of the wave function, and this explains also why it is sensible that the first derivatives of the wave function are continuous, because they form the probability flux, and the probability flux is expected to be continuous. Okay. Now let's continue. What happens when you integrate a continuity equation over a volume tau? This is visible at the bottom. When you integrate over a volume, you can exchange the time derivative with the integration over the volume. So the integral on the left-hand side, you remember that integrating psi modulus square over a volume is the probability to find the particle inside the volume. It is one of the initial information that we obtained from the Born interpretation, okay? So the left-hand side is the time derivative, or the change with respect to time of the probability to find the particle inside the volume. And this is equal if you bring the divergence to the right-hand side and then you integrate over the volume and then you transform it by the Gauss theorem into the flux. The change in time of the probability to find the particle inside the volume is equal to the negative of the probability flux across the boundary, which is perfectly reasonable. Okay? The probability to find the particle in a volume changes because there is a probability flux across the boundary, so that the probability may increase or decrease in time. On the other hand, if you extend the volume to infinity, the flux of J over the boundary must go to 0, because you extend the boundary to infinity and J is proportional to psi or psi bar star, so that j goes to 0 at infinity. Whereas the left-hand side does not go to 0 because it is an integral over the volume, okay? So you simply find that if you let the volume go to infinity, you find that the time derivative of the probability to find a particle anywhere in space, the time derivative is 0. So the probability, of course, is equal to 1 because of the normalization of the wave function, and the derivative of 1 is 0, which is perfectly normal, okay? So this result is also called the conservation of the norm of the wave function, but also this result is called the conservation of the norm, because the norm changes because there is a flux of probability across the boundary, okay? To conclude, we make an observation. If you look at the expression of J, it looks very complicated, okay? But it is not, because you remember a couple of lessons ago, let me note the page number. A couple of lessons ago, we introduced the momentum operator here, okay? The momentum operator is minus JH bar derivative with respect to xi. If you think of it as P1, P2, P3, so as three components, you have a vector operator that you may call the vector operator momentum, and it is obviously minus JH bar gradient, because you have d with respect to x1, x2, and x3. So minus JH bar gradient is the momentum operator understood as a vector, okay? So you see that in the expression of J, you have minus JH bar gradient. So here you have psi star times the momentum operator. And here you have the conjugate of the momentum operator. So you can write down J in a more compact form. You have psi star momentum operator operating on psi, and here you have momentum operator operating on psi, everything star times psi. So you have two blocks that are, as you remember, one is the conjugate of the other one. So the quantity in parentheses is 2 times the real part of one of them. So if we write it as such, 2 times and the 2 cancel. We have 1 over m, the real part of psi star psi, okay? For a moment, pretend that p is a number. It is not, but pretend that p is a number. It's a momentum as a number. Take it out. You have the modulus of psi squared. That is the density of probability, and momentum over m is the velocity. So it is like having velocity times concentration, that is the flux in classical terms, okay? This is not actually a flux in classical terms because there is an operator P. So we cannot take the operator out because the operator operates only on psi to the right and does not operate on psi star, okay? But formally, the structure of J is exactly the same structure of the flux. The flux, you remember, is concentration times velocity, okay, of classical mechanics or fluid dynamics, okay? So this equation has a deeper meaning, okay? It is exactly the same equation of continuity that we obtain with fluids or with particles like electrons or holes in a semiconductor, for instance, okay? Has the same meaning. So deep in the Schrödinger equation, there is a meaning of continuity equation. Okay, we shall not consider the case in which the Hamiltonian is related to a charged particle. We shall not consider the gauge invariance. And we have no time, so we shall deal with wave packets on Tuesday. Okay, so for the moment, I thank you very much, and we stop here.